of it. So if I take the gradient of this, I should get this. Check it for yourself. It should work. Okay, any questions? Sure?
For g of y,
Uh-huh.
say it wasn't just x squared and it had something else with it,
Yeah.
it would be the same concept though. As long as they cancel
Let's see if we can do one where that doesn't work out so nice.
Okay.
Yeah. I'm hoping that I have another example where that doesn't work out so nice, but something's telling me that we don't. Okay, so look, here's a great problem where, again, you can go down the wrong road on this problem very quickly and start thinking, second guessing whether or not you really should have taken this class. And then you realize, wait a minute, hold on, there's got to be an easy way. All right, so we're being asked to compute f.dr, right? f.dr. Here's our vector field. That look familiar? That's the vector field we just had, right? And we're given this curve right here. Your two choices are to go ahead and find the derivative of this, which would be your dr. And then you could plug in for x, t squared plus 1, and for y you could plug in t plus 2, right? And then you could dot the 2, and then you could integrate, right? You could do that? Do you all understand what I'm saying you could do? But that's way too much work. If I can somehow determine that that's conservative, right? If this is the gradient of little f, if that's what that is, then I know the answer to this is just little f evaluated at the two endpoints of the curve. In the previous example, we showed that this was conservative, right? And we found little f. And it turned out to be, you tell me I forgot, x squared y x ln x plus c, right? That's what it was. So that's from the previous example. So all I need to do is take that function and evaluate it at the two endpoints of this curve. So I'm going to need to know what is r of b, which this is the same as saying what's r of what? Two, because this is our b, right? This is our a. And what is r of 2? So plug 2 into this. What do you get? The vector 5, 4, understand? Then I need to figure out what r of a is. That's r of 1, which is the vector 2, 3. Okay? And so to answer this, I just need to do f of the vector 5, 4 minus f of the vector 2, 3. And we said a second ago that all that really means, right, is plugging in 5 for x and 4 for y into the scalar function. And then plugging 2 for x and 3 for y into the scalar function. What's going to happen? Any questions before I erase this part? What's going to happen to the plus c? They will cancel, right? So I'm going to continue this. This is equal to, let's plug in 5 for x and 4 for y. So 5 squared, 25, right? Times 4 is 100. Plus x, which is 5, natural log 5. So 5 ln 5. Plus some constant. That's what I get when I plug this point in. Then minus, now let's plug in 2, 3. So what would you get if you plug in 2, 3? 12 plus 2 ln 2 plus c, right? And when you subtract all these, the c's will go away, won't they? 100 minus 12, 100 take away 12, 88. plus 5 ln 5 minus 2 ln 2. You could leave it like that. You could also use properties and bring your 5 up, bring your 2 up, and then turn 2 logs into 1 log using subtraction, but I mean, we're there. So look, before today, right? Before today, if I would have put this on the board last class, without the fundamental theorem of line integrals, you would have gone through and plugged each of these components in for x and y, then dotted that with the derivative, and then set up the integral from 1 to 2, and then ground the whole thing out. This new theorem allows us to do it a lot shorter as long as we can come up with a potential function. But it requires it's conservative, right? No conservative, not conservative, no go. And you're stuck with the old way. So I believe on your take-home test, I do give you a vector field that is not conservative, that you have to do the hard way, the long way, and one that is. And you have the choice on that one. Okay, what we have not seen, all right, is how we would determine if a three-dimensional vector field is conservative. And I said, stand by, we will do that. But if it is, we still have a way of getting its potential function. So I'm going to tell you right now, this is a conservative vector field, all right? I'm going to tell you that. And what I'd like for us to do is go ahead and find its potential function. Let's go ahead and do it. Does everyone understand that you don't have a way of determining if that's conservative yet? Right? Okay. It's three-dimensional. All right, so what we know is that this piece is the partial of little f with respect to x. This piece is the partial of little f with respect to y. And this piece is the partial of little f with respect to z. Assuming that it is conservative. So I'll take that first piece of information I have, which is that the partial of little f with respect to x must equal 2xz plus y squared. Then what? What did we do last time? To find little f from that, we integrated with respect to x, right? So little f should be the antiderivative of this with respect to x, which is the same as the antiderivative of this with respect to x. So we're going to start building little f up here. All right, what is the antiderivative of 2xz with respect to x? X squared z. Everyone okay with that? What is the antiderivative of y squared with respect to x? Xy squared. Or you could say y squared x. Plus
Would we say g of x and y? Or z,
close. G of what could be over here that would go to 0 if we took its derivative? We could have a constant, we could have y's, we could have z's this time also, because there's 3 variables. So I'm going to put this. Yeah, g of yz. This right here is some function of y and z potentially that I don't know. For example, it could be y squared plus 1. It could be yz minus 5. It could be just 7, right? That could be a lot of different things, couldn't it? And if this blue was any of these, when I took the derivative with respect to x, I'd still get this. Understand? So I'm just going to call it some function of y and z. All right, what now? The next piece of information that we know is that the partial of f with respect to y has to be 2xy, right? So I'm going to take this and derive it with respect to y and set it equal to this. So the partial of f with respect to y, let's look at ours first. What's the derivative of this with respect to y? 0. With respect to y? 2xy. And then what's the derivative of this with respect to y? I don't know. G sub y. How about that? You see why I used that notation on the last one? Because on the last one, we only had one variable. It was only g of y. But now that we have two variables, it makes sense to talk about the derivative with respect to y since z is there also. We need that to be equal to what? 2xy. Ah, this one again is going to work out too nice for us. You see that? These have to be equal, right? The one that we know and the one that we're building from have to be equal. So I can get rid of that if you want to just look at it as an equation. Subtract, and you get derivative of g with respect to y must be 0. Which means that g of yz, this is a tricky one, right? G of yz, this thing we're looking for, when I take its derivative with respect to y, I need 0, right? I could still have a z in there. Couldn't I? How about just this? It's some function of z perhaps. Maybe that is a number. Maybe it's just 10. Maybe it's z squared, right? But it is definitely, I cannot say for sure it's just a constant.
But can we say g of y is constant?
We can, well, we can say, here's what we can say. This thing that we were looking at a second ago saying, hey, it could have y's and z's in it, I can say for sure it doesn't have y's in it. That's what I can say. Because when I take the derivative of it, if it had a y in it, the derivative of that would be 1 maybe, or right? Let's say it had 5y. The derivative would be 5. I need the derivative to be 0, right? So I know that there can't be any y's, but there could be z's. Because I took the derivative with respect to y and got 0, but all z stuff would go away, wouldn't it? It's a little trick. You got to kind of keep track of where you're going with this. Okay? Let me summarize where we are so far. I know that f, right, f turns out to be this plus this, but I know for sure now that that could, at the worst, have z's only. And maybe numbers, 5 or something, pi. Just can't have any y's. Now what? Use the last thing you know, right? This is the last thing you know. If I take the derivative of this with respect to z, I should get this. Do that over here. What is the derivative of the one that we're working on with respect to z? X squared plus h sub z, even though I could say h prime, because I know it's only one variable, but I'll do that, equals, what does it have to equal? X squared plus 3z squared, right? And this time we don't get 0, finally. Right? The x squareds cancel, and you get the derivative of h with respect to z is 3z squared. Questions? What is it that we wanted to know? Here's where we were, right? I wanted to know what this was, right? What is the h function? Not what is its derivative, but what is h? So why don't we integrate this with respect to z? What's the antiderivative on both sides with respect to z? So this is just going to be h of z, right? And this is going to be what? Z cubed plus, this time, c for sure. Because we know h doesn't have y's in it. You got it? It takes, the first time you do it, all right? The first one you do, when you come backwards, that constant is actually a function of two variables. The second time, it turns out in this problem, it was only a function of one variable. And then the third time, then you're finally at a constant here.
I have a notation question.
Yes.
So when you put the sub, doesn't that mean partial derivative all the time?
Yes.
Okay.
Yes, but look, let's say I give you some function right here and I call it f of x equals x squared. And then I write this down.
Yeah, well, I mean, that
That means the
matter
derivative,
because
there's only one variable, but this is correct notation still.
still
Yeah. This just means treat all other variables as constants, and there are none. So it's the same thing. If you go back and you look at notation from Cal 1 for derivatives, there's like 8 different ways you can say the derivative of something, and this is one valid way of saying it.
cool. I was
Yeah.
just
No,
confused.
Okay, so we ready for our final answer? It should be, this is where we were, right? And that h of z is going to be replaced with zq plus c. And what did I say the good thing about this is? When you're done,
Goes back to that.
you can check your answer. So take the derivative. Let's do it quickly. What's derivative of this with respect to x? 2xz plus y squared, zeroed out. Okay, derivative of this with respect to y? Gone. 2xy, zeroed out. What's derivative of this with respect to z? X squared, 3z squared, that's zeroed out. So it works. So you can always check your little f, the potential function. You can always double check it to make sure you got it right. Where's my book? I want to do another one. Those didn't seem very hard. Like, see if there's one that gets a little uglier. Okay, I have no idea how, if this, well, you know what? I think I have the solutions right here. Let me make sure. I'm trying to pick one that's going to get ugly so that you can see it happen. What's that? Process is the same, but we've been kind of getting lucky that these functions aren't mixed up. Like, you know what I'm saying? They keep on getting cleaner as we go back. They may get a little uglier. Let me see. All right, this one might work out. All right, get that off there. All right, so what if we have vector field sine y x cosine y plus cosine z, and then negative y sine z is our vector field. And I just want us to find the potential function. So I'm telling you that this is conservative, all right? So I will start by doing what? Okay, I know so far that this must be sine y, right? Integrate both sides. Little f must be the antiderivative of this with respect to x, right? What is the antiderivative of sine of y with respect to x? X sine y. X times sine y. Everyone agree? Plus, potentially here, y's and z's, right? That are mixed up somehow. So I put here what? Maybe g of yz. Let me make sure I copy this right now. Sine y, cosine z, negative y. Okay. Now what? Okay, so now I'm going to take derivative of this with respect to y. And the derivative of this with respect to y would be x cosine y, right? Because x is a constant. Derivative of that with respect to y. I just take derivative of sine of y, which is cosine y, and the x comes along. Plus what? Derivative of this with respect to y? G sub y. Understand? But that has to equal what? That has to match this, right? So that has to be equal to x cosine y plus cosine z, right? I don't like having this at the front, okay? Only because I have an equation, I'm going to work both sides of it. I don't like to have a string of equations and do that. But as long as everyone understands where these two pieces came from, right? All right, these cancel. And then you get g sub y equals cosine z. Now what? Integrate with respect to y. See, I'm trying to figure out what was that g function, right? What was it? Well, I know its derivative is this with respect to y. So to get back to g, I integrate. I'll show it this time. I integrate the left side. I integrate the right side with respect to y. The left side should just become the function g of yz. And the right side is y cosine z. Plus, it could possibly, because, yeah, we have to keep this all in mind. When we take the derivative of this with respect to y, we get back this, right? So if there was some stuff out here that had z's in it, those would all go to 0. So I'm going to put plus h of z. All right, we're getting there. Now, let's look at little f again. Here's what little f is. So I know that little f must be x sine y plus g of yz, which is y cosine z, plus some function of z. So each iteration of this, I'm kind of nailing down that function on the outside more and more. And I only have one more piece of information to use, right? That is that the partial of f with respect to z must be this, right? Okay, so let's take the partial of this with respect to z, which would be 0 negative y sine z plus h sub z must equal this right here, negative y sine z. It happened again. Oh well. But on the previous one it didn't, right? There was a little bit in there. All right, and then they cancel, so you get the partial of h with respect to z is 0, which means h of what? Only z. We know h is a function of z only. H of z must be then a constant, right? So you can go back right here, replace that with c, and you're done. So this is now c. There's your potential function. Everybody have a copy of the take-home? Look at number 4. Anyone need one? Yeah. I'm telling you on number 4 that that capital F is a conservative vector field. And I asked for part A for you to find its potential function. I spent a lot of time making that function.
So it's ugly as well.
So that when you have to do all this, it's going to require some work. Okay, some techniques of integration are involved there. So it's the same principle, just a little more challenging going backwards. All right? And this is a big hint, okay? A big, big hint. But after you do part A, part B is trivial. It really is trivial. Or you can make it a hard problem. It's up to you. For part B, you can make that real easy or make it real hard. You have to use the picture there to help you do that problem. All right, that's enough. I'm giving it away. So how many of you have taken a physics class and have ever heard something like, your work is always 0 on a closed curve if you've got a conservative vector? In conservative vector fields, your net work is always 0 on a closed path. Maybe. If you I mean, that's basically that theorem right there.
Something else. I forgot.
All right, we're ready to move on. This is the homework. By the way, I think 2 people responded. Kieran, you did it, and who else? The assignments. I sent a Jorge, right? Jorge did it first, right? You did it first. So I sent out a discussion. I said first 3 students to list out all the homework problems that I've given out this semester get bonus points.
Yeah, I think some of
There was 3. I deleted that one because it was a copy and paste. I could tell it was so obvious. Oh, this morning there was another one? Okay, so maybe not. All right. There was, I could tell that the 2 of yours were different. There were little things in there, but there was a 3rd one posted last week and it was an obvious copy and paste. So. All right. Move to the next section. We are in 13.4, Green's theorem. An entire section dedicated to one theorem. And this is a huge, like, fundamental result that we have here. And I think it's quite beautiful if you take a look at what it's saying. Green's theorem gives us a connection between a line integral around a simple closed curve and the double integral of the region bounded by the curve. So imagine, I'm sure I'm going to have pictures coming here soon. If I take a curve and I make it a simple closed curve, and I call that C, right? Then by default, it encloses a region, doesn't it? And that region I could call D. Green's theorem shows us that there is a connection between the line integral around this curve and the double integral of the region that it encloses. So remember, double integrals, you always had to have a region of integration. You know, we started with Cartesian, then we went to polar, right? Or we did Cartesian, then we did like type 1, type 2, then we went to polar, right? That was the double integral layout of things. Now, then we went to line integrals and we said, oh, we're going to move along a path and we're going to try and integrate along this path. This theorem ties the 2 together. They're actually related to each other, which is amazing. So we have to get some language down first. Positive orientation of a simple closed curve C refers to counterclockwise traversal of the curve. So if you're going to have a curve that's closed, right, then you remember the R of t draws it. Remember we came up with this, you know, R of t was usually the vector function that would draw the curve. Then, since it's closed, it's going to go around and come back to itself. we call positive orientation when you travel along the curve counterclockwise. That's positive orientation. If you go the other direction, that would be negative orientation. All right? So like this right here. R of t equals cosine t sine t. That should look familiar to you. T is between 0 and 2 pi. That draws us unit circle, positive or negative orientation. If you start t at 0 and go to 2 pi, it's going to go and draw it this way, right? That would be positive orientation. If you look at this right now, if you have a curve C that's oriented in the positive direction, imagine that you're on this curve, which is on a flat sheet of paper right here, and you're walking along this curve, right? I'm walking along the curve. The region D is always to my left, isn't it? As I walk around that curve, the region D is always to my left. Do y'all see that? Okay. That's another way to remember what positive orientation means. Your region on the ground that you're enclosing is always going to be to your left side. So here's Green's theorem. Let C be a positively oriented, piecewise smooth, simple curve. Okay, so positively oriented, counterclockwise. Piecewise smooth means that the curve might look like this. Okay? Maybe a bunch of line segments together, like this. Piecewise, it's smooth. So that piece, that's smooth. That piece, that's smooth. That piece, that's, you see it? So you could break up that C into a bunch of smaller, smooth segments. So as long as C is positively oriented, piecewise, smooth, simple, closed, which means I can't have a hole in the middle, right? You're in the plane, which means we're two-dimensional. This, by the way, this theorem will get extended out to 3 dimensions. Green's theorem is in 2 dimensions. When we move on a little bit further, next couple of sections, we blow this out to 3 dimensions. And it's got a different name. All right? So D is the region it encloses. And if P and Q have continuous partial derivatives on an open region that contains D, then here's the relationship between the line integral and the double integral. Okay, so here's the notation we have. Remember, this was line integral? And that curve could be any curve, right? If I want to tell you that it is closed, which means it comes back to itself, initial point and end point are the same, it means a closed curve, then what I do is I draw this little circle through the integral like that, and that lets you know that that C is closed. Also, there's no way that I tell you it's positively oriented. Okay? This is assumed to be positively oriented. If I want to tell you it's negatively oriented, going the other